Any questions on the PCB design?
So how do you want us to submit the files? Just post it to the website?
No, the Gerber file, you put them in the zip folder and send it to me by email. Yeah, I'm going to upload the Gerber file to the PCBWay website for you guys.
What time do you want that file?
By the end of the day, today.
Like 3 o'clock?
Before 12 a.m.
Okay.
Yeah. How many of you have worked with Arduinos in the past? I mean, how much, if you beginners, middle level beginner for? Okay. One? Okay. Okay, cool. All right. You? Beginner. Okay. So if you go to the website, because we have another 2 students, Sean and Michael, they have been in my Robotics Tool. So I've worked on these Arduino kits pretty intensively in the past. So that's why I assigned them 2 different projects. But for you guys, if you think you are still beginners, entry level, then I think these tutorials are good, pretty good. I have Arduino Basics. I don't know if this is too simple for you guys. This is just for the programming language, trying to be familiar with the programming language. So you know that the microcontroller, usually they run in a loop. So the setup function will be only executed by once, but the loop function will be executed forever as long as you turn it on. Okay, so you must know that before you move forward. And the Arduino IDE is free. You can download it from the website. It's used the C language, but also you can use C++. So these are the operators. I think you have taken C++1, probably 2 as well. So this should be very simple for you guys. Even though you haven't taken that in the past, these are similar to the MATLAB operators. Okay, and also Verilog as well. All right. This fundamental control structure: break, continue, do it while. And usually I don't use it, but since you have many other ways to do the same job. Switch case is very often used. Control structures, definitely the if statement, if something and do something. And you have if else. It's different from, it's the same from same to Verilog. If, else if, and else eventually. Okay. Integer. Just be aware of that. So the integer data type in different languages and different platforms, they represent different length. I don't know if you know that. So what's the length of the integer here in Arduino? I think it's 16 bits. In Verilog, it's 32 bits. It's very, I cannot remember all of these details. If I switch to another language and keep working on that language for 2 years, I will forget about everything else for the different language. So you just need to do a quick search. This is how things work. So for example, I've taught MATLAB for how many years? 2 years. The first 2 years I came over here. And now I pretty much forgot everything. But I was an instructor of that class. He was in my 104 class. Yeah, I was able to do that really well. But now forgot everything already. This is like your neural cells, your brain is being overwritten by other different languages. After MATLAB, I taught Python, and then Verilog. It's just overwriting all the old stuff. Okay, so this is you can make this into a forever loop, but while something is true, then keep doing it. So you can have a sub loop in the main loop of the program. For loop, it's the same as the C++ you learned. Just for you have an initial value, and here's a condition, and here's a operation. Okay, so if you didn't define the data type at the very beginning, you have to declare the data type inside the for loop. It allows you to do that. So assign initial value, and here's a condition, here's a +1, and assign it to 1. So it's incrementing by 1. Do you learn bit masks in C++1 or some other languages? Mask? No? It's just a bitwise AND logic. So for example, if I AND X and Y, what's going to happen here? It's doing a bitwise. So this single operator is doing a bitwise AND operation. So if you want, for example, Y is a mask now. I have 0 here, 0 here, 0 here, but all the other ones are 1s. So remember in the AND logic, if you AND something with 1, what's going to happen? Start changing that bit, right? But if you have a 0 here to AND whatever, it's going to reset it to 0. So the mask is actually doing, so if you are doing an AND logic, AND operation, so the mask here is literally just resetting these bits. Because whatever here, here, or here in the other number here, it's going to be reset to 0. But all the other ones are not being changed. So if you look at the result, this one has been flipped to 0 here as a result. And same here, same here, same here. But all the other bits are still the original bits from X. It's not being changed. So this has been used very often in microcontrollers. And you can imagine why it's doing that. Since you want to do a bitwise operation, and these bits, for example, the A bits, can be directly used to control the digital levels at the output. So for example, you have the Arduino board. A very, very simple application. Okay, so the board has, show it under the docking camera. So if you look very closely on the board, all right, and you can see that these are just the number 13, number 12, number 11, number 10, number 9, number 8, and to 0. Or these can be used as general purpose digital ports. Even though some of the ports have different functions as well. But however, if you want to just use my general purpose GPIO, that's what the GP means, right? General purpose IOs, input outputs. You can use these pins to control whatever, to turn on and turn off. Just send out a 0 or 1. For example, the number 13, okay? Number 13. I can connect it to a 200 ohms resistor and then connect that one to a LED and ground it. So if I assign a logic high to number 13, I'm able to turn on the LED. If I assign a 0 to number 13, it's going to output a 0 here and 0, 0, so there's no voltage drop, won't turn on LED. Okay, so the principle, the main principle of using microcontrollers to control digital system is literally just flipping the pins. If you flip them or toggle them really quickly, you can create different sequence of digital outputs, according to the timing diagram of the sensor or anything, so you're able to communicate with digital systems. Okay, it's very sweet and repeatable because the digital is way more reliable compared to the analog signal. If it's 1, it's just 1. If it's 0, it's just 0. Okay. Let's come back here. Sometimes you can assign the entire 8-bit number, binary number, to the 8 pins over here, from 13 to 5, 4, 6 probably. Right? If you connect each of the pin from 13, 12, 10, for example, until 6, and every single one is being connected to a LED here. Okay, for example. And if you want to create a pattern for the LED, only turn on the middle 2 ones of the LEDs. So you can directly assign the entire 8 bits to the register which controls the pins. And you don't have to, write a 0 or 1 to every single pin. You can directly just write an 8-bit binary number to it. And how to create that pattern really quickly? You can directly use the mask to reset some of the pins, right? Just give a 0 to it and do an AND logic. It's going to do the job really quickly for you. This is just a very simple example, and it's being used everywhere. So the mask can be used in the AND operation, but also the OR operation as well. So for example, I want to really quickly set. So set means pull the pins to logic 1. So for example, if Y is the mask, then I want to set bit 6, and this is bit 4, and all the other bits as well. Set these pins to logic 1, so I just need to OR X with this mask, which is Y. So I can set here to be 1, and here to 1, here to 1 as well, but keep all the other pins as original value. Okay? So that works. And left shift, if I shift Y to the left by 1 bit, then this becomes, so this one here will be shifted out, and it's gonna make up a 0 at the bottom, at the right hand side. So it becomes 0, 1, 0, 0. That's a left shift operation, and similar to the right shift operation. So if I shift this one to the right hand side by 1 bit, what's gonna happen? This 0 will be shifted out. And you have to make up a 0 over here, so it's going to be 0, 1, 0, 1. 0, 1, 0, 1. All right, make the connections through the USB port. So if you look at the board, here's a USB cable, even though it has a different shape, but all the pins, all the voltage levels are the same for any types of USB cables, like for this one, or for the micro USB for your phone, or for the USB cable for the iPhone's cable looks a little bit different, but they're all the same, 5 volts, keep in mind. USB whenever 5 volts, okay? And this is able to communicate with the computer, so you have your script written in the Arduino IDE and upload the code to the CPU here, or to the microcontroller over here. And it's being converted. So the USB protocol is being converted into UART. So we're going to learn UART in CE351, but now we just use it. We don't need to find out what's happening in UART. All right. So the USB data is being converted into UART by this chip, the USB to serial. So UART is also being named as serial communication. It's confusing because not just the UART is serial communication. SPI, I2C are both serial communication, even USB. So what USB stands for? Universal Serial Bus. So it's also a serial communication. So compared to parallel, what are the advantages of the serial communication? So what is a parallel communication? If I have 8 pins and I want to communicate with another chip, also has 8 pins, and I directly short them together, all right, and I can communicate from here to here. So how do I do that? There must be a clock, right? I can send at some moment the data. There's a data pattern over here for the 8 bits, and I just need to send a signal to let the registers over here to receive all the 8 bits of the digital numbers. So the advantage of using parallel communication, as you can see, this is a totally parallel, is this is very fast. You can do this really fast compared to serial because you can communicate, you can send 8 bits to the other side at the same time. It takes less time, only 1 clock cycle. So everything will reach the other side. So what about serial? Usually the data pin is only 1 or 2, sometimes let's just say just 1. So this is out, this is in. You definitely need a clock. How this communicates from here to here has to follow a certain timing diagram. So it's literally inside here. Usually it has a shift register, 8 bits, for example. That's inside this chip. And the serial data will be received by the MSB over here, and it's being shifted down. So this pin is here, right? So this is sending bit by bit to here. And after this one receive it, you have a rising edge over here to send it to the other D flip-flop. And then keep shifting to here. So eventually, you need 8 cycles to receive all the 8 bits because this is being shifted down. So eventually, you got D7, D6, D0 being stored inside this receiver. Yeah, 8 different cycles, 8 cycles. Because every cycle is going to trigger the transfer from D to Q, right? Doesn't like this one. You have 8 D flip-flops, it's parallel in, parallel out. A lot faster compared to serial, because this one needs 8 cycles. Because you don't have connections to here. This is the only connection that you need 8 cycles to shift all the data down. And then you got all the 8 bits available inside the device over here. You can do whatever computation you need. You can send all the data, all the 8 bits to the CPU for computation, adding, subtracting, all this kind of operation. But you have to pump all these single bit binary numbers into the device first. Okay, but still, I'm not saying like which is more popular because both are being used everywhere, but in different situations. For the serial, usually it's being used for chip-to-chip communication. The reason we prefer serial communication is because it's saving a lot of pin resource. If you look at this board, how many pins do you have? Not too many, from 13 to 1 to 0. Only 14 digital GPIOs. So if you use 8 of them to communicate with one device, and you only has probably 5 left to communicate with another sensor. So sometimes you probably need like 20 sensors being connected to the microcontroller. So it seems impossible to make it work, right? So that's why for microcontrollers, if you are communicating with a sensor, usually we prefer serial communication, saving a lot of pin resource on the board. However, if everything has been received by the chip inside the device, you prefer parallel communication. That's why in here you cannot control it. You cannot change the internal structure. This is how you can. Why it's so awesome to learn IPGA and microcontroller in the same semester, so you can tell the difference. After the data is being received by the CPU, you cannot modify the internal structure. You're just writing a very higher level C++ code in order to process the data in here. But however, you don't know if it's parallel or serial, inside. But in FPGA, you can modify the very bottom level digital circuits. You can directly have a bracket, right? And have 7 colon 0. You know it's parallel. But here it's different. That's why people are claiming that IPGAs are faster than microcontrollers. There are 2 reasons. First, you can do parallel computation inside IPGA. This is general purpose microcontroller. You cannot modify it, the internal structure. Okay, whatever. So the logic has been synthesized by the engineers from ML, which is acquired by Microchip a couple of years ago. But anyway, so the digital design engineer in the company already wrote all the Verilog code and synthesized all the code into the digital blocks, and then sent them to TSMC for fabrications. Then you got this. All right. IPGAs are different. So 2 reasons that IPGAs are faster than microcontrollers. First, you can do parallel computation internally. Second, usually the IPGAs are newer technology. Doesn't like this one. This is 350 nanometer technology, very similar to the 500 nanometer technology, which was like 60-year-old technology we have been using. And they have been, I'm pretty sure they are manufacturing how many, like millions of these chips for this kit, right? For general purpose, for fun actually. But IPGAs, they may have newer versions because they change the design faster than this one. And so the IPGA board you guys are using are probably 20 nanometer technology inside. So you can compare 20 nanometer for the minimum length for every single transistor compared to 350 nanometer. It's a huge difference. So you can use a faster crystal oscillator for the IPGA, but this one is only, if you look at here, because you have huge transistors, you cannot run them faster, that fast. So this is 16 megahertz. 16 megahertz. But IPGA you guys have, the basis rate, it's not even the advanced one, it is running at 100 megahertz, about 6 times faster, because transistors are smaller. Okay. And another thing is, because this is a mixed signal design, so mixed signal is not the pure digital chip. It also has ADCs inside. It's a STAR ADC actually. You guys have designed a similar one in your class. And so the ADCs have op-amps and all the analog components, which cannot be fabricated using the newest technologies. The digital, usually they can be used for digital designs like the 20 nanometer technology, 25, 22. These are being used for digital design, which is fine, but for analog, you just cannot use that small transistors. I think like 65 probably is the smallest you can use for op-amps. So that's another limitation. So these are the reasons why IPGAs are faster than microcontrollers, but sometimes it takes a very long time to design a system using an IPGA embedded system. It's a lot easier just directly use this one because all the libraries are, most of the libraries are available online. Other people already developed the libraries, can directly just call the function and receive the data from the sensor. It's going to be very difficult to develop all the things from scratch using IPGA microcontroller because you have to design all the drivers by yourself. You have to interface with the timing diagram with every single sensor on your own. It takes a lot of time. All right, let's go back to the tutorial. So definitely go through every single step over here to be familiar with the programming language for Arduino. So the serial print is printing that character to the serial monitor on your laptop. So it's actually communicating directly internally and to the laptop through the USB. So it's sending the character through the USB to the laptop. So that's why you can see it on the monitor. So serial.begin defines the UART communication baud rate, which is the speed, how many bits per second. So it's 9600 bits per second. And you can tell it's very slow actually. But for very simple application like that, it's good enough. Okay. So if you look at this very simple example, setup. So the setup function will be only executed for once, keep in mind. Okay. And so that's why you don't have to keep setting the baud rate again and again, because you just need to set up that. It's like configuring the speed of the communication, just need to do it once. And the loop will be executed forever as long as you keep the Arduino board on. Then after this part of the code is done, it's going to keep running this from top to bottom and then come back to the top. It's being executed forever. Does that matter? You assign 1 to A every time when it's come back to the top and then executing every single line? Doesn't matter. You just keep assigning this. So this one, the serial.print is going to send C to the serial monitor so you can see it. And then serial.end is going to terminate the serial communication. So that's why even though you have this forever loop, it's running back and forth forever. But however, since you end it, that's why it's only printing one character over here. Okay, that's how you can control the number of how many of these characters you want to send to the serial monitor. Even though you have a forever loop, you can end it. Okay. So a quick question. The serial communication is ended. So see this in a serial monitor on the laptop. Are these instructions are being executed still after this is being printed on in a serial monitor? Yes. The forever loop is running inside the Arduino microcontroller, so it's keep running. Some very similar examples. Definitely recommend you guys to try it out. Else if statement, try it. So it's different from writing all this code in MATLAB on your desktop, because everything is being executed on the board. It's not being executed in the CPU in your laptop or desktop anymore. Keep in mind. So this will be the computer runs all this code. Shift your mind from the previous pure computer science programming to this hardware programming in the future. Always think about hardware when you're programming microcontrollers. These are trivial, I think. Okay. There are some tasks for you guys to work on. All right, and another thing I want you guys to remember actually. So the color code for the resistors. I'll probably give you a very simple quiz on it. Maybe Friday. So which color represents which number? So black is 0, brown is 1, red is 2, orange is 3, because you have all the resistors in the box and they have been used already. So it's just everywhere. It's going to be a pain if you don't know which is which. But I'm going to give you a portable multimeter so you can measure the resistance as well. But it's still very beneficial if you understand the code, if you know which represents which number. Okay. So for the four of you guys, I have 1, 2, 3. And it's due next Monday because these are very simple tutorials. I think Monday is too soon. I think probably I'm gonna make it due next Wednesday. Okay, I'm gonna change the deadline for this task. And on Wednesday, I'm gonna explain some of the techniques being used in this tutorial. But now I think it won't take too much time for you guys to finish the Arduino Basics. You just need some really simple snapshots that demonstrate that you have run through the examples over here. And then here, LEDs. So number 3 is actually digital pin 3 on the board. That's what you guys know. Sometimes it sounds weird, right? You just put a number there. So number 3 means digital pin 3. Keep in mind. And the pin mode, you can set LED, this variable, which is actually 3, the pin 3, to be an output. It's going to run as the output mode. And then it gets into this loop, forever loop. Digital write, it's going to write a logic high to pin 3 and delay for 100 milliseconds. So 100 has a unit of ms, millisecond. And then digital write LED low. So after 100 milliseconds is 0.1 second. So pull it high, and after 0.1 second, pull it down, and then wait, and then come back. So it's actually blinking the LED. So it's going to blink this LED. And you always need a resistor to protect it. It doesn't have to be 300 ohms. It can be 1K. It's going to be just a little bit dimmer compared to 300 ohms. It can be 300, 220, 400 ohms. It doesn't matter at all. But you do need a resistor to protect it. Otherwise, the internal resistance for the LED is very low. It's going to draw a lot of current, and it's going to blow off the LED. And you have you can have a few LEDs being controlled by 5 pins in parallel, and you need a protection resistor for each of them. And the push button, keep in mind, if you flip it, you can see that this plastic line indicates these 2 pins are being shorted together, but these are not. So it's literally just has 2 wires, one here, and 4 pins. So know how to plug that into the breadboard. So a resistor to protect it, and a push button connect this LED to 5 volts. And if you press a push button, then what's going to happen? LED will be turned on, and here's 0 volts. Why is this not 0 volts over here? So if I keep this switch, if I don't press the switch, so it's disconnected from here. What is the voltage here? Why? Yeah. So what's the voltage here? Always 0, right? And there's no current, so no voltage drop. That's why 0 volts, right? And 0 volts, and here's nothing. Definitely, there's no power. It won't turn it on. So what's the name of this resistor here in this case? It's called pull-down resistor. It's pulling this pin down to the ground. And there's another one which is called pull-up resistor, like this one. So if I do not press this push button, then what's going to happen for this pin? 5 volts, right? Because there's no current, it's disconnected, no current, no voltage drop, 5 volts, or 5 volts. So this is called pull-up resistor. Why? Because it's pulling this pin up to 5 volts. Okay, same here. So this resistor is pulling. It's a little bit confusing. Why is this pulling? It's not pulling. This is a resistor. It's a passive component. Why is pulling? Okay, it's just a name, right? This resistor is pulling this pin to the ground, and this resistor is pulling this pin to 5 volts. So this is a pull-up resistor. This is a pull-down resistor. So I have a little control using the Arduino. So these are 2 separate circuits. Okay. So this push button is going to send a 0 signal to the pin, one of the pins of the Arduino, like pin 3, and you have to write an Arduino code to sense that. It's like an if statement, right? So if this one becomes 0, then I'm going to turn on this LED, which is controlled by the other pin. You know what I mean? So it's not directly controlled by the push button. You have to write a little Arduino code to control it. Get it? So this pin is shorted to pin 4. This pin is shorted to pin 3. So there's no direct connection from this push button to the LED. It has to be controlled by the code. Do this. So what about this one? It is originally on, right? Oh yeah, you're right. Actually, sorry. To press it, it's going to short this to the ground, and then it's 0. It's going to be off. Yes. Okay. And there's no Arduino, right? Nothing can be controlled by Arduino. But you use Arduino, you can definitely use the same connections you did in the previous code. What is this asking to do? But just read this code and see what's doing here. So 3, 4. Read it. If it is high, then write a high. If it's anyway. Schematic. Is this the same as the previous one? Oh, it's just different logic. Now it's high. If you read the 0, you can turn off the LED. Okay, very simple tasks for be familiar with Arduino code. And SSDs, 7-segment display. There are two different types of SSDs. So this one, the one you have in your box is a common cathode 7-segment display. So you can see the cathode is being shorted together. So you can control the anode in order to turn on and turn off the LEDs in the display. Okay. You may have seen this somewhere in your life, but just look at the internal structure of it. It's very simple. So here's a pin out. What does COM mean? So that's a device, right? Here's a pin out. So COM is the common mode, the common cathode connection. So if you look at this pin out, actually this pin and this pin, they are shorted together and shorted to here, to all the cathodes of the LEDs. So every single bar is LED, right? And that pin is being shorted to the cathode of every LED. And so you can control these pins in order to make a pattern to show a different number on the display. A, B, C, D, E, F, G. Okay, it follows the order from the top LED and eventually get to the middle bar here. So it's A, B, C, D, E, F, G, like that. A quick question here. If you want to show an 8, number 8 on the display, what are the voltages over here? Should be. dP is a point, a decimal point. Here's a little point over here, okay? So if you want to just to show 8, number 8, without showing this dP, what are the digital values for each pin over here? Say it again? Yes, and you want to ground this pin. So it's number 3 and number 8, they have two common cathode pins. So just ground these two and give 1s to all these pins. And don't forget to use protection resistors for these displays, like this. Okay, connect the resistor to each single LED.
Why is that pin on top grounded?
You don't need another 8 pins to be controlled if they only need one same voltage. You only need to control one pin, one terminal, because the other terminal will be the same, just running currents through different branches. If you want to run, because you can control one terminal here, right, separately, so don't have to control every single one here as well. So the purpose is just to turn on to be able to control each single LED. Okay, by doing that, you can definitely control every single LED without using 16 pins, but only 8. Okay. This is the common cathode. You may have seen a 7-segment display device, but using a common anode, which is actually the 7-segment display on your Basics board. Which means all the LEDs are being shorted as an anode, but you are controlling every single cathode. So if you want to turn it on, you need to set that pin to be 0 in order to turn it on, right? So you have 2 different ICs. There might be more than 2 ICs in your box, but definitely you want to read the print on the top to make sure you are using the correct IC. So the decoder is 4543 in a box, and that decoder is being used to reduce the number of pins being used for the from the Arduino board. Why it works? Since now you can see that I have to use 8 pins to control every single LED on the display. So what if I have multiple digits of the displays? It'll be a disaster. I don't have that many pins over here to control another display device. So using a decoder is one of the solutions if you only have one display and you want to keep the cost low, because you know that to have 8 different outputs, you only need actually 3 inputs. Because 3 digital inputs can give you 2 to the power of 3 combinations of the outputs. From 000 to 111, there are 8 combinations. You just need to design the digital circuits inside the chip. Actually, we have the commercial decoder for you, so you just need to use it, plug into the board and use it. So the 3 digital inputs can give you 8 different combinations. You just need a 3 input pins to give you 8 different results, right? And there's another chip, is 595, and keep in mind, don't use it for this decoder application. Make sure that you are using the correct chip. So the 595 is a shift register. I'm going to explain that on Wednesday. So by using a shift register, you can just use 1 pin, the data pin here, to display a number onto your display device, 7-segment display device. And that's it. Okay, so if you have 4 digits, how do you show different numbers on every single one? Just 2019, So you have to use a shift register to make it happen. I'm going to explain how to use it on Wednesday, but I think you are good to start working on the Arduino Basics over here and also the LEDs as well. Yeah, I think I will probably give you 2 weeks to work on the 3 tutorials over here. Okay, so it's going to be due next Friday. I'm going to change the deadline here to next Friday. Okay. Makes sense? Any